Okay, g'day students, and welcome to lesson 10. Today we're looking at indicators. The point of today's lesson is that we want you to be able to understand that an acid-base indicator is a weak acid or a weak base, where the components of the conjugate acid-base pair have different colours. So the acidic form is different colour to the basic form. I should explain the relationship between the pH range of an acid-base indicator and its pKa value, and then recognise that indicators change colour when the pH equals the pKa, and identify an appropriate indicator for a titration given equivalence point of the titration and pH range for the indicator. So first of all, indicators are large organic molecules from certain plants. So you might be familiar, for example, with red cabbage and hydrangeas. I always think of old ladies when I think of hydrangeas. I don't know why. They can change colour depending on what you put in the soil that they grow in. So for example, if you want hydrangeas to grow blue, you can put some sulphur in the soil and that'll turn the soil acid. Or if you want it to be basic, you can put in some other chemicals. So lime, calcium hydroxide for example, and it will turn a pinker colour. So you can change the colour of these plant petals based on the pH of the soil. Now, indicators are weak acids or bases. The conjugate acid is one colour and the conjugate base is another colour. So there are different pH ranges of indicators. So if we have a look here at the acid form of an indicator, we can see that here's our acid form of the indicator. You can see that H for the proton, and here's our indicator, and here's a conjugate base over here. So you can see that, for example, if we're looking at thymal blue, we can see that on one side we've got one colour, so that would be the one side. Oh, well, we've got over here a different colour. If we've got bromothal blue, we've got the acid side and the base side. So you can see that the colour that indicators change is different, and it's based on the acid or base form of that indicator. So we also have a dissociation constant for the indicator, and that should be fairly familiar with you now. And you can see that we've just put the IN there to represent this here and this here. Okay, so if I think about colour changes, the indicator changes colour when the concentration of the acid, or the acid form, there we go, equals the concentration of the base form of the indicator. So the colour change occurs when the concentration of the hydrogen ion equals the acid dissociation constant. And that therefore we can think that the pKa value is equal to the pH. Now to get the pKa, just like we get the pH, so remember that pH is what? The negative log of the concentration of the hydrogen ion. So it follows then that the pKa is just a negative log of the acid dissociation constant. Now if we have a look at methyl orange here, we've got a pKa of 3.7. So what you'll see here in your exam situation is this data table, so 3.7. You can see here we've got a pH range of colour from 3.1 to 4.4, and it goes from red to yellow. So let's have a look at your textbook. So we've got methyl orange, and you can see here that we have a transition around the midpoint here. So we'll just have a look at the bottom left before we get on to transition. So when the pH is greater than the pKa, that's going to be an acid form, and so the methyl orange is going to be red. If the pH is less than the pKa, that's the base form of the indicator, and that's going to be orange. And now the range for methyl orange is that 4 weak acids. You can see that it's 3.1 to a pH of 3.1 to 4.4. Now A transition point is just a midpoint of that color change. So we can see that that's around here. So that's our pKa as well, isn't it? So when the concentration of the acid form equals the concentration of the base form. So in this case, it's pKa of 3.7. Therefore, the concentration of the hydrogen ion is what? 10 to the negative 3.7 moles. The general rule of thumb for a transition point as the midpoint is just plus or minus 1 pH value. So that in this case, if the pKa is what, 3.7, it's just thinking transition from 2.7 to 4.7. It will transition through. Now there are some indicators that you'll be familiar with. So universal indicator is, you would have grown up using that quite a lot, and it's quite handy because it's got a wide range. It's got a pH range of 1 to 14, but it's a combination of a variety of different indicators. It's not as accurate as, say, a pH meter, and there are some other indicators that will change colour at more precise values as well. Now, bromophil blue is an interesting one, so we'll look at that one first of all. So bromophil blue is what you can see is it's yellow in acid, it's green when it's neutral, and it's blue in basic solutions. So let's have a look here. We said that the hydrogen form, so the acid form of the indicator and is in equilibrium with the base form. And if we have a look here, we've got adding acid to the solution. So if I'm adding acid, I'm going to shift this equation to the left. Now if I'm going to add hydroxide, I'll shift it to the left and it will appear yellow. So we've got our yellow one over here. We're producing a lot of that. So remember Alder-Chadeleu's principle and disturbing equilibrium as well. Now if we're adding hydroxide, we are shifting it to the right, and so we're going to end up with a lot more of the base form of the indicator, and so the bromophil blue solution will appear blue. Now methyl orange, we talked briefly about, that's suitable for what? Weak acids. And phenolphthalein. Phenolphthalein, that's a tricky one to spell, that's always good for hangman. You can see here it's suitable for weak bases. Now the equivalence points is where we're heading with this, and the end point. So this is a very important concept for you to get your head around, especially when we move into volumetric analysis and titrations. So indicators are useful for finding the equivalence point in neutralization reactions. So remember, a neutralization reaction is when you add an acid and a base together. You're going to get a neutral solution. So if I add a strong acid and a strong base, well, I'll get a neutral solution. And in this case, it should end up at a pH of 7. Now that equivalence point is the moment during a neutralization reaction when the acids and bases are in the stoichiometric ratios as represented by the reaction equation. So what is this saying? This is saying if I've got 1 mole of hydrochloric acid and 1 mole of sodium hydroxide, I should end up with 1 mole of sodium chloride and 1 mole of water. Now that should tell me it's at a pH of 7. That's a strong acid and a strong base. And notice that it's a monoprotic acid and the base only denotes 1 hydroxide as well. So if I'm looking at a titration curve, and this is probably the first time you would have come across this, you can see a titration curve, a strong acid being added to a strong base. So let's have a look what we start off with. We've got a pH of 14. So this is starting off with a strong base down the bottom. So if I have added a indicator, it's going to start to change colour through this area here. And it's going to change colour very rapidly. And this is important because this is a sharp endpoint. So the endpoint is when the indicator changes colour. Now it's desirable to have a very sharp endpoint. So when one extra drop will have a marked colour change on the indicator. because that's just going to make it easy for us, isn't it? So if I'm looking at bromothor blue, for example, it's going to turn green at a pH of 7. So bromothor blue could be an appropriate indicator to use, and we could determine that endpoint and the equivalence point as well when one additional drop causes a sharp change in the colour of that indicator. So it's desirable to have a sharp endpoint because it's going to make it easier to determine the pH value, and see, we can calculate the concentration of the hydrogen ion then. So we've done a little bit today. Have you understood that an acid-base indicator is a weak acid or a weak base, and that the components are a conjugate acid-base pair that have just different colours? Can you explain the relationship between pH of the acid-base indicator and the pKa? And can you recognise that the indicators change colour when the pH equals the pKa? And identify an appropriate indicator for a titration given the equivalence point of the titration and the pH range of the indicator. When you're good with that, please work on the mastery exercises for today.